We are going to discuss the goals of parallelism. In the world of computing, we often ask, why do we go through the trouble of designing complex parallel systems? It isn't just about raw power, it is about efficiency, cost, and reliability. Over the next few minutes, we will explore exactly what we aim to achieve when we move from sequential to parallel processing. Let's start with the big picture. What is our core definition here? Parallelism means performing multiple tasks simultaneously using multiple processors or cores to improve overall performance. Instead of relying on a single brain to do all the work, we employ a team. We have identified 7 main goals that drive the adoption of this technology. 1. Increasing speed and performance. 2. Efficient resource utilization, so no hardware sits idle. 3. Scalability, allowing us to grow. 4. Higher throughput. 5. Cost effectiveness. 6. Solving complex problems. 7. And finally, ensuring reliability and fault tolerance. The first and perhaps most obvious goal is to increase speed and performance. The fundamental logic here is simple: we execute multiple tasks at the same time to finish work faster. Imagine you have a massive project. In a sequential world, you would have to do step 1, then step 2, then step 3. Parallelism allows us to divide large tasks into smaller parallel tasks. By attacking the problem from multiple angles at once, we drastically reduce the total execution time. A perfect real-world example of this is video rendering. If you try to render a high-definition video on a single core, it might take hours. But if you use multiple cores, different parts of the video are processed simultaneously, allowing the render to complete much faster. Our second goal is efficient resource utilization. Modern computers are powerful machines, often equipped with multiple processors and cores. A major goal of parallelism is to ensure we use all available processors and cores effectively. If we run a standard sequential program on a supercomputer, most of the machine does nothing. Parallelism prevents the CPU and memory from being idle. It ensures that the hardware you paid for is actually working for you. This involves balancing the workload across processors. We don't want one core sweating while the others sleep. By distributing the work evenly, we maximize the hardware's potential and increase overall system productivity. Next, we have scalability. In the tech world, demands rarely stay static, they grow. Scalability means that performance grows when more processors are added. This is crucial because it means our systems can handle increasing data and workload easily. If your website suddenly gets double the traffic, or your dataset doubles in size, a parallel system allows you to simply add more hardware to cope. This supports system expansion without a performance drop. We don't have to redesign the software from scratch, we just scale up the hardware. This capability is critically important for large and evolving applications like social media platforms or scientific research databases. Closely related to speed is the goal of higher throughput. While speed focuses on how fast one task finishes, throughput focuses on quantity. It is about completing more tasks per unit of time. Think of a busy highway. Speed is how fast the cars move, throughput is how many cars pass a specific point in an hour. Parallelism widens the highway. This improves productivity, especially in multi-user environments where many people are trying to access the system at once. This is particularly useful for servers and cloud computing. These systems need to handle many jobs simultaneously, processing thousands of requests from different users without becoming a bottleneck. Moving on, we have reduced response time. This is all about user experience. Parallelism gives faster results for individual tasks. When you click a button or run a command, you want the result now, not in 10 seconds. This improves the user experience significantly in real-time applications. Consider gaming or simulations. If the physics engine, the graphics rendering, and the AI logic can all run in parallel, the game feels smooth and responsive. It is also vital for online systems where lag is unacceptable. By processing data in parallel, we minimize waiting time, making the interaction feel instantaneous. Now, let's talk about the bottom line: cost effectiveness. You might think adding more processors is expensive, but it is often cheaper to use multiple small processors than one massive, super-fast processor. Building a single processor that is twice as fast is incredibly difficult and expensive due to physical limitations. Connecting two standard processors is much easier. This approach also reduces power consumption and overall hardware cost. It improves performance without requiring expensive upgrades to bleeding-edge technology. Organizations get a better return on investment by clustering standard, affordable hardware to achieve supercomputer-level performance. Our final, and perhaps most critical goal for essential services, is reliability and fault tolerance. In a single processor system, if the CPU fails, the screen goes black. The system dies. In a parallel system, the system continues even if one processor fails. Because the workload is distributed, the other processors can pick up the slack. This provides backup and ensures uninterrupted service. This improves system safety and dependability. This is why parallelism is used in mission-critical areas like medical systems, aerospace, and banking. In these fields, downtime can mean lost lives or lost fortunes, so the redundancy provided by parallelism is non-negotiable. In conclusion, parallelism allows us to build faster, cheaper, and more reliable systems that can grow with our needs. Thank you for your time.